Right, welcome back everyone. Last time I promised that today I will talk about the cosmological constant, the dust solution with cosmological constant. Actually, I decided to postpone this a little bit and to dwell for 45 minutes with a solution without a cosmological constant. What I want to derive today is a so-called Mattich formula, which played an important role in the history of cosmology, and in particular in view of if you come from the field equation, if you are a relativist, if you view at cosmology from the viewpoint of exact solutions, then I think the Mattich formula is really remarkable. It's an exact equation for the relation between luminosity, distance, and redshift. So in this class of spacetimes, you can write it to all orders in an exact expression. Derivation is not quite simple, so it will take a while, but I think it's worth doing it. So we will again look at these solutions which we had last time. So these were the dust solutions without a cosmological constant. There were three types. If the density is high enough to produce a recollapse, then it was a cycloid. If it is a borderline, so this was for k equal plus 1. The borderline case is k equals 0, where the universe just escapes to infinity. This is tangent here to this. And if the density is overcritical, so that's what one calls the critical density, and if it's overcritical, then I have a universe with k equal minus 1, and the scale factor safely escapes to infinity. And the differential equation, which we had to solve, which we did solve actually, was the Friedmann equation for this case, equate over c squared a of t. And on the right hand side we had this conserved quantity with a dimension of a length. You see, this is dimensionless, this is a length, so this must also be a length. And it is a measure for the mass. Yeah, so the conservation law was a mass conservation law. Okay, and from this equation I claim one can derive a relation between distance and redshift which is exact. And this is really remarkable because it will involve only you may choose at a time, an instant of time, say now, and then you need to know the Hubble constant at this point, which gives you information about the pitch of the curve, and the deceleration parameter, which gives you the curvature. And these two numbers, with the help of these two numbers, you can write down a formula which applies to all three cases, which relates luminosity, distance to redshift to all orders. So the distance between observer and emitter may be arbitrarily large. Of course, if you just want to do it up to second order, then it's a triviality that it works, right? If you give the first and the second derivative of the thing, then of course the Taylor series is determined up to second order by these terms. The remarkable thing is that it is determined to all orders, and it is exactly so it might be considered similarly to those of you who know the multiple moments of the Kerr metric. The Kerr metric had infinitely many multiple moments. All of them are different from 0. But the first two, the mass and the angular momentum, determine all the higher ones. And here it's exactly the same way. The Hubble constant and the deceleration parameter determine all the higher order terms. Okay, and that's what I want to derive. Unfortunately, it will take a little bit. So I have as a preparation, I have to derive three equations, which we will then use later. The first one comes from this, is if I solve this for a prime. So from this, of course, I find that a prime squared is, if I multiply this to the other side, c squared over a of t a naught minus k a of t. So a prime of t is c times the square root a naught over a of t minus k. Okay, that's the first equation. That was not too difficult to derive this. Let's call this E1. I will derive three equations which I then use. The second equation involves the second derivative. So if we differentiate this equation, so that's actually the second Friedmann equation, which, or it's equivalent to the second Friedmann equation together with this here. Let's differentiate this. Then I get k a prime of t plus, oh no, let's differentiate this here. This is nicer. Let's differentiate this equation. Then I have 2a prime of t a double prime is c squared a naught. This comes with a minus sign, a prime of t. And generically, a prime of t is different from 0. We are not considering static solutions. And okay, the solution may have an extremum, but this is an isolated point, so we can assume that generically a prime is different from 0. So this
be plus and a k.
With a sign.
Get a minus sign from the derivative and a minus sign from the bracket.
Let me see. I differentiated this equation here.
Yeah. In the bracket, the first term vanishes.
But the k term is constant if you optimize.
No, I differentiated this here. I differentiated this here. 1 over a squared with a minus sign and then a prime. I think it's correct. And I'm fairly sure a double prime should be negative. Yeah, it's a decelerating universe what we are talking about. Okay, and from this I get the deceleration parameter. Actually, how was it defined? So Q of T naught, if you remember, was this here, divided by prime of T naught squared, and we have calculated these expressions, so I can insert this now. Do I want to do it in this way? Let me check what I want to derive, that I get the right thing. Yes, that's what we have. Exactly, very good. So this should be a naught minus k, yes. So this is minus a of TO, a double prime I've just calculated, so this gives another minus sign, so we have a plus now. A naught, there's a 1/2, a of T naught squared, and a prime squared is up here. So this is c squared over a of TO root, no, it's squared. AO minus K, A of TO. Okay, can we simplify it a little bit? So this goes away, and this goes away, and we have A naught over 2 times A naught minus K, A of TO. And maybe let me solve this for this expression here. So I can write this in the way, let's take the inverse. The inverse is 1 over 2q. Then I get a 2, this divided by this. Gives, no, I put the 2 on the other side. What did I do now? Yes, I multiplied the 2 on the other side, and then I take the inverse, and I get a 1 here. I get a 1, this divided by 1 minus k A of TO over A naught. That's very nice, yes. So actually the form which I use then later will be an expression for this here. K A of TO over A naught is 1 minus 1 over 2 QTO. That's our second equation. Then I need a third one, which allows me to express the scale factor in terms of the Hubble constant, among other things. Let me check, what did I use? Yes. I'll write this in a somewhat more complicated way. A of TO divided by A prime times A prime. So there's no doubt that this is correct, right? Why do I do this? Because this gives me the Hubble constant. This is A prime TO divided by the Hubble constant. And for E prime we have this expression over there. A prime with this here. So this is C over H of TO square root AO over A. I do it at the point TO minus K. Is that it? Let me take a root of K out of the bracket. I don't care at the moment whether K is positive, 0 or negative, so this might be an imaginary unit here. yeah, if k is minus 1, but the equation is correct nonetheless, then I also get from this root something imaginary, so the whole thing will be real. A of TO, is that it? Yes, A of TO k minus 1. Why do I do this? Because this is exactly the expression which I had calculated here. Is it this? Well, actually it's it's the inverse, right? It's the inverse. Yeah, okay, then it's the inverse. C root k divided by h of TO. And this expression here is the inverse of what we have calculated here. So it's 1 over 1. 1 over 1 minus 1 over 2q minus 1. Okay, can write this on a common denominator. Then I have c root k h of TO. I write everything upon 1 minus 1 over 2qto. Then I get a 1 minus 1. This goes away. Minus minus gives plus. So this gives 1 2qto. And my final formula, that's the third formula which I wanted to derive, is that this is just root k h of TO, and I multiply this out, and then I get 2q TO minus 1. Okay, that's the third formula. And I have to be careful not to erase them, because I will need all of them in a minute. Okay, what do we want to calculate? We want to calculate the relation between luminosity distance and redshift. So what's the luminosity distance? We had a formula for this. The luminosity distance, the idea was we observe an object in the sky, and we associate with this a distance measure which is inverse proportional to the brightness. Yeah? And the formula we get, that was a universal formula for dl, which we just derived, or rather we we derived it from a geometric consideration. It was that it is A of TO, the observation event. Then there was a factor 1 plus z, taking care of the fact that the energies, that the photons lose energy when they propagate. This is a redshift factor. And then we had this function which I always called eta of chi. That was the formula, the general formula for the luminosity distance. And what we did before was we developed this into a series in that. And what we do today is, with the help of the field equation, with the help of this differential equation, which we have used here, we will derive an exact expression for this in terms of z. So this is constant, the observer is fixed. Yeah? So the emitter may be at any point where he wishes to be. So this is fixed. Here we have directly the dependence on z. So the task we have to do is we have to express this in terms of z. Yeah? And that's not easy actually, this will take a while, but I hope I will manage to do it. Let me remind you what the eta was. So eta was a function which was sine chi, or sinh chi, depending on whether k was plus 1, 0, or minus 1. And there's a way to write this in a common formula. I could have used this already before, I haven't done this, but for this derivation it's very convenient. I claim that this can be written at sine root chi, root k times chi divided by root k. So that's obviously true for the k equal plus 1. Yeah, because then I have exactly this expression. It's also true for k equals 0. Then I get it by a Bernoulli-L'Hopital rule. Yeah, and I write this as a Taylor series. Yeah? This begins with root k times chi and then the higher order terms. So it gives a chi in lowest order and the rest goes away if I send the root of k to 0. And here I get an I. If k is minus 1, here I also get an I. So both expressions are purely imaginary. The quotient is real and it's precisely the sinh. Yeah? So that's a way of writing this formula in a compact form, where all three cases are covered simultaneously. Okay, and that's what we have to calculate now. Well, we have to recall what the chi was. The chi was he has a co-moving distance between the two world lines, emitter and observer, and it was given by an integral emitted time, observed time, CdT over A. Yeah? So the situation is this: here you have an observer, here you have an emitter. The emitter sends a light ray, and here we have the time TE, and here we have the time TO. Of course, it's not a straight line in general. Yeah? It's maybe arbitrarily curved depending on the scale parameter. In order to solve this integral, I make a substitution, and well, in the shorthand notation, this means I write a dA in the numerator and in the denominator. Yeah, that's a substitution. Yeah? I substitute for t the new variable a, so then my boundary values are a of te and a of to. Why do I do this? Because for dA by dt, that's a prime, I have an expression. This is E1. So that's the reason why I derived this equation. So I now use E1, and then I get an integral a of te, a of to. I have c, no, this is gone, dA over a, and here I have dA by dt, and this is the square root with the c. The c and then the square root of a naught over a minus k. So the c, the factors of c cancel, and I can pull the a under the square root, maybe then it's nicer. There's a bracket missing. A of te, a of to. Then I get root a naught a minus ka, a squared. Yeah? And that's an elementary integral. If you have under a square root a quadratic expression, that's elementary. If you have a cubic term or a fourth order term, then it's an elliptic integral. If you have just something quadratic, then it's an elementary integral. So you can either solve it with a substitution, or you can look it up in Bronstein. I did the latter. And what one finds is it's 1 over root k. So it's written in a form which works for k equal +1, -1, or 0, where in the case that it's 0, you have to use always a rule of Bernoulli-L'Hopital in order to evaluate the expressions. And for the case k-1, you get an imaginary quantity divided by another imaginary quantity, so that everything is real. Okay, what was it? The arc sign. Arc sign 2ka over a naught minus 1. So that's what Bronstein gave me. And of course I have to evaluate this for these limit values. Okay, let me push this up. So what we are calculating is chi. Let me multiply the root of k to the other side. And then I get what? Then I get the arc sign of 2a, and now I'm at the point TO over a naught. No, the k is upstairs, sorry. K is here. Minus 1. Minus the same thing with TO replaced by TE. 2a of TE divided by a naught k. I leave a gap here. Minus 1. Well, TO is constant. Our observer is fixed. Yeah, we have a fixed observer, and we consider different emitters. So the TE is the variable. And the TE is related, of course, to the redshift z. In the our final goal is to derive chi as a function of z. Yeah? And the z is hidden at the moment in the TE. Yeah? Because it depends on where the observer is, what the redshift is, and what the TE is. So I want to get rid of the TE, and I want to have the redshift in the game. So it's a very good idea to multiply numerator and denominator with a of t naught, because then I get a redshift here. A of te divided by a of to is just a redshift factor, and this is a constant. So we have now a very nice expression, sine 2a of tok over o minus 1 minus arc sine. And this here, A of TO divided by A of TE. That's a redshift. 1 plus Z. Yeah, that's a redshift formula for Robertson-Walker universes. A 1 plus Z is A over TO, A of TO divided by A of TE. And what is left is 2K A of TO minus 1. And now you see why I calculated this expression here, which this equation which I called E2, because that's precisely the expression which we have here to evaluate. So I now use E2, and then I get, so what is this? There's a 2 in front of it. Apart from this, it's precisely this expression. Yeah, so I have to multiply this with 2, then I get 2 minus 1 over 2QTO minus 1. That's the first bracket. And the second bracket, arc sine, again with a 2, but this time also with a 1 plus Z in the denominator. So I have 2 minus, there's a 2 gone. I multiplied with 2, yeah, sorry. I multiplied both expressions with 2, so I have 1 over Q of TO here. 1 minus Q of TO minus 1. Yes, that's it. Okay, can write it a little bit simpler. 2 minus 1 is 1, if I'm not very much mistaken. And what is this? A minus. So can I do something with that? Yeah, I think I can write it on a common denominator. So I get 2 minus 1 is 1, minus 1 over QTO, and the Z comes with a minus sign. That's it. Okay, so I have expressed my chi in terms of Z. Everything else is constant. Yeah? So, of course, I want to write this in a nicer way. Actually, the expression we want to evaluate, it's up there in the first line. I have the eta, and the eta is the sine of this here. So I need to calculate the sine of this. So let me call this for a moment alpha. And this beta, then we have found that the sine of root k of chi is sine of alpha minus beta. Yeah? And well, that's one of the trigonometric identities which I know by heart. This is sine alpha cosine beta minus sine beta cosine alpha. And I know what alpha and beta are, so I can insert this here. So sine of alpha means the sine of this, so the sine and the arc sine kill each other, so I just get 1 minus 1 over QTO. That's this term, sine alpha. Then I need the cosine of beta. Well, I have the sine of beta, but the cosine, of course, is root 1 minus sine squared. And the sine is this here. The sine is this here. So it's 1 minus 1 over QTO minus Z. That's not a 2, it's a Z. You should be careful with my handwriting. 1 plus Z and the whole thing squared. Yeah? This is the sine of alpha. This inside the bracket is the sine of beta. So the square root is a cosine of beta. And then minus sine beta. This is this expression in the bracket. QTO minus Z over 1 plus Z. And the cosine of alpha is root 1 minus sine squared. 1 minus 1 minus 1 over QTO squared. Well, and now we are on a good way. Everything looks fine, and I think we will have the result soon on the board. So, can we simplify this a little bit? Well, I think I calculate the expression which we actually want to have, namely the dl. The dl is A of TO, 1 plus Z. And for eta I write the sine divided by the root. Sine root k pi divided by the root. So up to the factor A of TO, I have to multiply this with 1 over Z. So let's begin with A of TO. And then let's multiply all this out with 1 plus z. So I leave this as it is. 1 minus 1 over q of TO. Actually, one often writes q naught for this expression, but let me stick with the notation I have used it. And then I multiply the square root with 1 plus z. So I get under the root 1 plus z squared. And here the denominator is cancelled. So I get minus 1 minus 1 over qto minus z squared. That's the square root. And here, just this factor, 1 plus z is killed. Minus 1 minus 1 over q of to minus z. Can I simplify this a little bit? Yes, I think I can multiply. I can use the binomial theorem. So I get 1 minus 1 is 0, plus 2 over q, minus 1 over q squared. And that's it. And well, that's a formula, right? We still have to work with this here a little bit. I haven't used A3 until now, so I will now use A3. But before doing this, maybe I pull a q squared out of everything. So then it becomes nicer. So I multiply the expression in the curly bracket with q squared. So one factor goes into this. This gives a q minus 1. And the other factor goes into this. This gives a q squared under the square root. So I get, I can multiply this out, right? Let me see. Are the signs correct? 1 minus q minus z? Minus. Yes, yeah, it's okay, it's okay. Yeah, okay, let me just write the q factor. So I have to multiply this out. Yeah, let me write it this way. TO squared, and then I multiply this out. So I get 1 plus 2z plus z squared minus 1 minus 1 over qto squared minus z squared. And then the mixed terms plus 2 over qto plus 2z minus z over qto. Oops, bracket closed, square root closed. So hopefully we get rid of a few terms. This cancels, this cancels. Anything else? No, I think that's it. Okay. And here I also pull one factor, one of the q factors into the first bracket, and I get q of to minus 1 minus z q of to. And the other factor I pull into this bracket, so then I get 2 q of to minus 1. And I strongly hope that I can extract this square root from both factors. Let me see. Let me write it again. Then we see if it works. Of to squared, q of to minus 1. So what is this here? This gives a minus 1. This gives a plus 2q. This gives a plus 2z q squared and minus z over q minus qto minus 1 minus z qto and the square root. Now let's see if I've made everything correctly. My claim is that this factor is also contained in this. Let me try if this is true. FT naught, let me pull this bracket out of the, this square root out of the curly bracket. Q of TO squared. Okay, then certainly nothing happens with this term. Let's see, here I have this term once. And here I have it multiplied with 2z. Is that 2? No, with z. So under the square root I have minus 1. And here I have plus z q of TO. Is that true? If I multiply these two square roots out, I get minus. No, I think the sign is wrong, right? Let me see. I get the minus 1. I get the plus 2q. I get the 2q squared z. And I get the minus, what's wrong here?
Why is there still divided by q of TO? If you multiply everything with q of TO squared in the last term, it should be also something.
You mean I made a mistake here?
Yes.
Okay, let me check. Minus 1. This is this term here. 2q, it is this here, right? 2zq squared minus, this is upstairs, right? This is upstairs. Yes, thank you. Does this help? Let me see. 2z minus, yes, this helps very much. Now it works. Now it works. That's precisely what I have here. Excellent. So I think I managed to derive the Matic formula. So the only thing which is left is to insert E3. Yeah? The factor in front of everything is very similar to the expression on the left-hand side of E3, on the right-hand side of E3, or rather multiplied to the other side. So if I insert for A this expression there, then I get C root K over H of TO. I think I forgot every time this term here, this root K. It's there all the time, root K, root K, root K, and that's very good because now it cancels. So what was I writing? A is C root K over H, and then this square root 2QTO minus 1 comes from the A, and another time it's already there. So almost everything cancels, no, not everything, but several terms cancel. And we are left with this expression. Okay, you might say the derivation was maybe not particularly entertaining, but the result is really remarkable. So, well, it's usually written in a slightly different way. So if you want to compare exactly with a Matic paper, I think rewrote it in this way. So one usually begins with this term here, that Q of TO, and the other two have a common factor, namely this factor, Q of TO minus 1. Let's make a square bracket, and then I have the square root Q of TO minus 1, and that's it. So dl is a function of that. An elementary function. There's nothing more complicated than a square root in this relation. So that's the Matic formula. And it was derived in a paper by the Potsdam astronomer Matic in 1958. Actually, it was in one of the books I read when I prepared this lecture. I even read the word Matic revolution. Maybe that's a little bit overdoing it, but it was an important feat because actually it was the first time that this whole business of solving Einstein's field equation was directly related to observable quantities. Yeah? So the Friedmann solutions are around since 22, 23. And people started intensively talking about distance redshift relations, say in the late 20s, Lemaitre, Hubble, and so on. This was 30 years later. And this was the first time that the two things really were combined in terms of an exact formula. That you started with an exact solution to Einstein's field equation and derived the relation between observable quantities from this. And in this sense, I think it was a remarkable result. From our present point of view, of course, you could say we don't believe anymore that this is a realistic model for our universe, because now we believe that we have, at least in addition to what is there, the cosmological constant, or any other version of dark energy. So in this sense, we don't take this for the whole story anymore. But nonetheless, this dust component is an important component, and studying its behavior is certainly also reasonable from the present point of view. So let me again point out what we see here. The Hubble constant is in principle a measurable quantity. The acceleration parameter is in principle measurable. If you just determine them if you have standard candles, then you can, from the observations, you can determine these two numbers, and then you can check if they are related by this formula, and then you can verify if this is a good model or if it's not a good model. I should have emphasized that the Q is positive for all these models. Actually, you see it in several places. The equations simply don't make sense if Q would be negative, and it is never negative because all these models are decelerating. So if you compare this with the data we have now from the supernovae of type 1a, then we can certainly say that this is not satisfied. So it's not an agreement with the idea that we have a positive Q. And so in this sense, comparing the supernovae 1a data with this formula clearly shows that this pure dust model doesn't work. We need something else. Okay, I think we will do a little bit with the MATI formula in the worksheet, so we can discuss, of course, the behavior for big Z and for... The remarkable thing is that the K has dropped out completely. It's a universal formula for all three cases. During the derivation, we always had the K flying around, but in the end it cancelled. It's the same formula for all three cases. That's also remarkable. Okay, I have 5 minutes left, but I think I leave it with that. So as I said, we will talk about this in the tutorial next week, and on next Tuesday I will then briefly discuss the dust solutions with cosmological constant and some other perfect fluid solutions. Not give a full discussion of this. This will then become too big a field, but I will single out a few important ones. Certainly the radiation cosmos, and certainly the dark energy case with the W equal to -1. So these two cases we will certainly do, and maybe a third or a fourth. And so I think we will finish the Friedmann solutions in the course of next week. And then we will talk about observations and linking all these mathematics really to the observations which we have to date. Any questions to this derivation or to other related things? If not, I wish you a happy weekend, and we continue with the tutorial.